Hello, everyone. Welcome. I think we'll go ahead and get started. Thank you for joining today's webinar, Lessons Learned from a Decade of Gravel Wetlands. Here at the New England Environmental Finance Center, we're excited to present this webinar in partnership with the University of New Hampshire Stormwater Center and also Lake Champlain Sea Grant. A few logistical reminders before we get started. We are recording this meeting. We'll also post it to the New England EFC's YouTube channel afterwards. You want to share it with others. We do anticipate somewhat of a large group today, so please stay muted, but feel free, personal preference if you want to have your camera on or not. It's nice to know who's in the virtual room with us, but we also recognize this is lunchtime, so whatever is best for you. And we will have some time at the end of today's talk for a Q&A. So we'll be using the Q&A feature in Zoom. If you're not already seeing that on the bottom of your Zoom screen, you might need to click on More, and then you should see the Q&A option there. Feel free to add your questions in there at any point during the talk, and we'll get to them at the end. All right, next slide, please. So I'm Chloe Shields. I'm the Deputy Director here at the New England Environmental Finance Center. And along with my colleague, Matt Duff, we're representing our New England Water Infrastructure Network, or NEWIN program today, which I'll speak a bit more about in a minute. But wanted to share a little context of how we came to host this webinar. And it really came out of an opportunity we had this summer to attend a Green Stormwater Infrastructure Field Visit Day organized by Jill Sarazin at Lake Champlain Sea Grant. We got a chance to go up to Shelburne, Vermont and observe firsthand with a number of neighboring community public works staff and municipal stormwater coordinators, multiple different approaches that Shelburne was taking to managing stormwater in their town. So we saw bioswales, rain gardens, some underground storage, and also gravel wetlands. And the gravel wetlands really stood out as something where the participants were interested in learning more, and also something that we know from Jill has really been proliferating in Vermont. So Jill will introduce her work briefly because we know there are a lot of Vermont folks on the call, and then we'll turn to our featured speaker, Dr. Jamie Houle from the University of New Hampshire Stormwater Center, who has been studying gravel wetlands for a decade now. And then to wrap up today's agenda, I'll hand it back to my colleague, Matt Duff, who will highlight just a couple new, or a couple not necessarily new, but existing funding sources for these and other types of stormwater infrastructure projects. Next slide. So if you're not already familiar with the New England Environmental Finance Center, we work across all 6 New England states. We're supported largely by the U.S. Environmental Protection Agency with the mission to build community capacity to fund and finance environmental priorities. So you might know us from some of our existing programs. I know there's a lot of folks from Massachusetts and Rhode Island on today's webinar who may have worked with us through our Southeast New England program or SNEP network that's focused on resilience and watershed management and stormwater, or our NEWIN program that I already mentioned, and we'll tell you a little bit more about on our next slide. So our New England Water Infrastructure Network, the goal is really to support municipalities, water utilities, public water systems to access funding for, could be drinking water, wastewater, certainly stormwater and non-point source pollution needs, primarily through state clean water and drinking water revolving funds, but also other sources. We are a network, so it's not just the New England EFC. This is one of the ways we've gotten to know the UNH Stormwater Center very well. They're one of our core partners in this network. And together we provide one-on-one technical assistance to these water systems around financial, managerial, or kind of specialized technical knowledge to help address their water challenges and move them towards funding and implementation. And we're always looking to collaborate as a way to connect to new communities and to leverage each other's expertise. And Lake Champlain Sea Grant is a great example of one of those collaborations where we've got to know more communities in Vermont. So I'll hand it over to Jill to just briefly introduce herself and say a bit about her program before we move into Jamie's talk.
Awesome. Thanks, Chloe. Wonderful to see many familiar names here today. My name is Jill Sayers. I'm with Lake Champlain Sea Grant and Vermont DEC. And as Chloe mentioned, we've been working with the UNH and UNH Stormwater Center teams to bring stormwater training and collaboration to Vermont over the past year or so. My role with Sea Grant is to bridge the gap between research and application, and we do that through collaborations, trainings, and site visit days, such as the one that Chloe mentioned this summer with the town of Shelburne, where we visited several gravel wetlands. I also supported work to generate research-based guidance for soil media, which you'll hear a little bit about today from Jamie. As many of you know, gravel wetlands are becoming increasingly common across the state, and we've heard lots of interest and great questions. So we're really glad that Jamie is willing to do a deep dive today on their work monitoring and promoting these practices. And I'm also always looking for more suggestions for trainings and collaboration, so feel free to reach out. Now I'll pass it off to Jamie Hooley from the UNH Stormwater Center. Thanks, Jamie.
I think you're on mute, Jamie.
Thanks a lot. Yeah, thanks for having me. It's great to be here. And gravel wetlands or subsurface gravel wetlands are one of my favorite topics. It's something that we started testing when the Stormwater Center first started in 2004. And as you'll see, it's one of our best performers. So, if you're not familiar with a gravel wetland, it's largely a two-cell horizontal flow subsurface wetland system. And I say subsurface because there's really not a standing water on the surface in the basin geometry where the water quality volume is stored. All the action is happening underground as it travels horizontally through this network of gravel that is interspersed with the dangling roots of the different wetland plants that are growing in the system. So it's great if you have the space. And when we look at the overall performance from a hydraulic perspective, it's hard to beat. What you're seeing here is a typical influent hydrograph, followed by the brown, which is a effluent, the hydrograph leaving the effluent. And the reason why it's so metered is because it's all controlled by a subsurface orifice. And we'll get into the details. Really, the two big things around gravel wetland installation are ensuring that you have low conductivity subsoils, such that the water is traveling in a horizontal direction as opposed to a vertical infiltration direction, and it's construction of a outlet control with a orifice that drops this the internal storage or with the basin storage within a 24 to 48 hour period. So when we look at, sorry. All right, when we look at the water quality treatment, as I said, it's probably our top performer. It might only be rivaled by, say, a permeable pavement system where the vast majority of treatment we're expecting happens through infiltration into the native subsoils. But from a actual chemical processing, this system by far is one of our top performers. And when we look across the range of unit operations and unit processes that the system employs, it hits about every one known in the stormwater engineering world. So everything from settling in the forebays to vegetative uptake to microbial mediated denitrification in the subsurface saturated zone and absorption and others as well. I think it's the microbial aspect in the subsurface that is really doing the bulk of the work. But suffice it to say, if we had one system to install and we had the space, it would probably be a subsurface gravel wetland. I don't know why okay. Sorry, my cursor was on the wrong PowerPoint. I should at least note that everything that I'm going to say today is embodied in our gravel wetland specification, and we do update that periodically. So the last update was 2022. We're getting ready to update it again with a lot of the phosphorus testing criteria that Dr. Eric Roy and Dr. Elizabeth Hurley have come up with at the University of Vermont. So we do work closely with Vermont, and I think Vermont holds a special place as probably the earliest and most prolific adopter of subsurface gravel wetlands as a treatment system. So when we look at the range of different treatment characteristics, of course, we're looking at that water quality volume, which is largely still how we're designing a system, although that's slightly changing. So when you look at resources like the Southern New England Program retrofit manual and even the most up-to-date New Hampshire manual, you'll see some variability. We're transitioning to use of the performance curves that are embodied in Appendix F of the Massachusetts and New Hampshire MS4 permits as a way to really quantify the performance of our structural controls. And so when we move towards more quantified characteristics for stormwater control measures like 90% TSS reductions, 60% phosphorus reduction, and in coastal areas, a 50% nitrogen reduction, we're really using those performance curves to dictate the sizing necessary. And that gives us a lot more flexibility, particularly if we're a little bit limited on the land. So in a lot of state manuals, the water quality volume still persists, but I just mention it because we're sort of transitioning as the research improves. We also are concerned about channel protection volume. So typically we go with the Q2 or the 2-year return interval storm event, and we're trying to maintain the pre and post peak flows associated with that so that we're not inadvertently scouring downstream stream channels. And so that is still a requirement. And this is all, again, done in the outlet structure. And then we can do extreme storm volume control or peak flow control. Not much volume control in a system like a gravel wetland, largely because of the impermeable subsoils. But we can use the basin geometry and the outlet structure to control the 2, the 10, the 25, the 50, and the peak flow. All right, so pre-treatment is one of those things that we've kind of changed our opinion on. In most stormwater manuals throughout New England, a structural forebay is required. We've seen problems even within our gravel wetland systems of that structural forebay, sometimes being designed dry, which is necessary in the subsurface gravel wetland, but often operating wet due to settling or, other things that may be happening in that forebay. So we've been, even though in the stormwater manual, they might call for a volumetric forebay design size for the 10% of the water quality volume, we have allowed for things like upstream, offline, deep sump catch basins to provide that pre-treatment. This, at least in New Hampshire, requires a waiver from alteration of terrain, but oftentimes that's no problem. We know that functionally the forebay really is there to provide a quick and easy accessible area for more routine maintenance. So that's really the ultimate goal. And then the two treatment bays size for 45% of the water quality volume each. And again, I'll go over some questions. There's been a lot of discussion around why 2 treatment cells. And the short answer is because that's what we studied. This was originally borrowed from the Georgia State Manual. And And that's just what was constructed. So with infinite time and resources for research, we definitely would have studied a single cell, but I don't see any reason why you couldn't. A single cell gravel wetland wouldn't have the same performance of a double cell. Other kind of design elements that have changed over the years is that we used to have a length to width ratio requirement, and we got rid of that after seeing some of the funky geometry. Our New Hampshire Department of Transportation, which has also installed a lot of these up and down 95. So the length to width ratio is really an artifact of maybe some of early detention pond design, and we really don't see it necessary in gravel wetland. And that, again, what does that do? It opens up some flexibility to configuration. So we can make these more linear and less wide, and they can fit various more locations. And for DOT, it's very important since they exist in a linear kind of environment. So geotextiles is something we've found early on, at least in the vertical cross section, we don't like to do that just because if they're unmaintainable, they tend to clog. Underlying soils, again, for the subsurface gravel wetland, should be have low permeability, and that's to force that horizontal flow. We've also updated our guidance for any subsurface underdrains across any structural control to at 8-inch minimum pipe. And that's mainly more for maintenance access in the post-construction condition. So again, I won't go into too much detail, just limited on time, but a lot of this information is in our specification. But the general anatomy of a gravel wetland is a 30-foot travel in the subsurface of stone. Could be 3/4-inch stone, that's most typical, but we've also seen a range of different stone varieties. The key is that you have this intermediate layer, which is this pea gravel, and it creates a setting bed that allows the more fine materials above it to set above more coarse materials. So there is some variability within the specifications of the stone layers, but typically it's a 3/4-inch stone that's widely available here. And with that intermediate layer being a pea stone or 3/8-inch stone. And then, of course, the key is all in the outlet structure. If you don't have low permeability soils, you might consider using a different system. If you need nitrogen control in particular, we've been modifying bioretention systems with internal storage reservoirs, which provides the same denitrification as the subsurface gravel wetland. And I'll show you a little bit of some of the advancements with the hybrid systems at the very end, time permitting. All right, so pre-treatment, I discussed that commonly. A volumetrically sized forebay, but there are other options. I don't want to limit your creativity on only volumetrically sized forebay. One of the other areas that we've innovated is around the hydraulic inlet. And so if you think about the muck soil, as the Vermonters call that wetland soil, the topsoil, the muck soil, it's really critical that we get that right because, again, we're not trying to promote vertical infiltration. If that muck soil is too permeable, say your typical bioretention soil, then you have potentially short circuiting of the plug flow path, which is really important to a horizontal flow gravel wetland system. And when I say plug flow, I mean we are creating a hydraulic inlet at the front, and we're trying to push water through horizontally in the vertical direction in the subsurface. If we have too much infiltration, say down at the end of our system through the soil, then that's interrupting and short-circuiting our plug flow conditions, which we feel is very important to the overall treatment performance. So we used to use perforated lines as the hydraulic inlets. They can clog, and we noted a need for redundancy in these style of systems, as it's very hard to maintain these perforated risers. So we've since kind of modified the inlet. So where you have your inlet pipe into your gravel wetland area, we've modified that with a splash pad with 4 to 6 inch large diameter stone overlaying a woven geotextile. There are lots of reasons why we use woven geotextile. I won't get on my geotextile soapbox because that'll take a lot of time, but we use woven mainly for durability and maintainability. We can remove that 4 to 6 inch stone periodically, and then we replace that woven geotextile over time. So that's been the big modification on the hydraulic inlet. And I'll talk about the muck soil layer. That's an area of continued research and development. And I'll go into that a little bit later. The next and almost most singularly important area is the design of the hydraulic outlet. So if nothing else, if you have low permeability soils, oftentimes, that's a difficult thing for engineers to develop stormwater management in areas with poor soils. It's very, very amenable to the use of a subsurface gravel wetland. If you don't have those soils, you'll need some type of liner. But outside of that low permeability native soils, we have the outlet structure, which does pretty much all the rest of the work. And in the outlet structure, we have multiple flow controls. The primary flow control is going to be this low orifice that will be sized to drain the water quality volume or the upstream retention volume in a 24 to 40-hour period. And that outlet control, the invert of that, is going to be elevated so as to maintain a internal storage reservoir of water. And that internal storage reservoir is key because in between events, it takes a lot of the oxygen that's in stormwater, and it drives down through microbial activity to anaerobic conditions. And it does that relatively quickly, like within hours of a storm event. We'll see that oxygen that comes in during a storm go down to about around 2 milligrams per liter of DO, dissolved oxygen. So really important for that denitrification to happen. So that's why we maintain that internal storage reservoir. The next kind of controls are, again, to control the channel protection volume. You'll have another outlet control. Sometimes that's a weir, and we're showing kind of a weir in this outlet structure. So that'll be designed in the secondary control to bypass that Q2 event. And then you'll have some high flow contingencies as well. Let me go into the next. One of the big innovations we've come up with the outlet control. And this is mainly from inspection and maintenance of these systems. It's really important when you're designing your outlet control to maintain it's like the clean side of the orifice should be maintained from only receiving clean flow. And I have some pictures to show you some of the mistakes that we've made. Well, and the reason being is that orifice control can sometimes be as small as an inch. And if you have water coming into your outlet structure that's skimmed from the surface and might have organic debris, or it's kind of conveyed from other areas that have higher core sediments, that outlet structure could clog. So it's really important that on the clean side of that orifice control, you're only getting the flow from the underdrain of the gravel wetland. So it's filtered flow only. And so you could have a solid access cover on the clean side that for maintainability or inspection, but your graded drain is on the dirty side of the orifice control so that any debris or organic material that's getting in is being flushed through the high flow outlet, right? And it's not getting stuck on the clean side of that orifice control. And this is by far the most problems we ever see. Most often we see a structure like this have a graded inlet across the whole entire top. So if the grade's going across the whole entire top, now you have the opportunity for debris, small aquatic invertebrates, frogs to get down in here and potentially start to clog the orifice control. So as far as inspection and maintenance, that is the number one thing that is maintaining this orifice. And the best way to minimize that is to have a configuration like I'm showing here. And again, that's all in our specification. And just some pictures of some of the wrong ways that we've done it. Here you're looking at this is the so the gravel wetland is in the foreground here. Obviously, it's discharging to the wetland towards the top of the picture. That's the high flow bypass. There's the channel protection volume weir, and you have the orifice control here that's regulating flow within the gravel wetland, which is yet to be constructed. And then we put this kind of box high flow bypass. So in the event that the system itself had filled up, water could convey over into the outlet structure through this kind of box cutout weir. And the problem there, of course, is in addition to the flow, you're also getting anything else being skimmed out the surface, right? Like I said, vegetation, soda bottles, pop bottles if you're in the Midwest, or any other trash or debris or anything else can float to the clean side of the orifice. That's the thing we're trying to correct. And there it is with the high flow bypass. We got the graded inlet here, right? But again, we would minimize or eliminate this altogether. And alternatively, you can put that bypass in the notch that in the side of the structure here, or you can provide another contingency for high flow bypass around the structure itself. So there's other ways to do it. Just do not let dirty water on the clean side of that orifice control. Outside of that, there's really not much to it. There are additional criteria, again, for the muck soils. Again, if you, this specification is on our website. It's also in the new New Hampshire manual that just came out in February. In addition, I know that Vermont has specifications for this as well. And I think I looked at them in preparation for this, and they're basically the same. The difference is updating the testing of the wetland soil with respect to the phosphorus, the soluble reactive phosphorus, and using more of the Malic 3 digestion in order to assess that. And I'll go over that a little bit later. So the wetland soils covering the surface should have low permeability as opposed to what we commonly prescribe for bioretention soils. And again, the idea here is you want horizontal flow through the stone. You don't want vertical flow through the soils, which is the complete opposite of how we design bioretention, which are more vertical flow dominated. So early on, we said, this should be a mixture of everything. Compost, sand, silt, clay, and with that clay component not exceeding 15% by volume, we were worried about cracking potentially of that soil with greater clay content. So this is, the issue. If you just use like a straight up wetland soil, you could get, as the system dries out, which is prone to do in this type of application, you could get cracking and opening of surface cracks on that wetland soil, and thus short circuiting of your horizontal flow path. So this is kind of the science in trying to get the right mix, 10 to 20% organic matter by mass. We've seen all kinds of different things as far as that wetland muck layer. In the subsurface, it's a lot easier. We have this 8-inch thickness of a wetland soil minimum. Then we have a 3-inch intermediate layer, often just pea gravel. And then we have a minimum 24-inch gravel in the subsurface. So pretty easy to construct from the bottom up. Some of these surface infiltration rates are the harder targets. And so, we've been told it's very, very hard to meet a specification like this. And I think as long as we can get close, we know that this is going to clog up over time. And the key is the use of geotextiles. I think we don't want geotextiles in the vertical cross section of, say, a bioretention, because we're really worried of clogging. But here too, you think about it, you have wetland plants and you want those roots to to go into the saturated zone in the gravel subsurface, and a geotextile, could potentially block those plants, or at least not facilitate their migration into that internal storage reservoir. So we don't like the use of geotextile. Like I said, we got all kinds of mixes. The most humorous one we got is they prescribed gravel, that pea gravel, all the way to the top, and that certainly is not something that we're looking for. The other issue we've seen is potentially people mixing existing soil from other sites, which I think is a great application here, but they could have rocks or other woody debris. And we rejected a couple of soil samples with huge, like 3-inch boulders. And, a 3-inch boulder has a risk of potentially bridging that 8-inch minimum wetland soil. Or things like logs. We had logs in there too, that, big branches, 6-inch diameter branches that were, feet long. And again, when we have stuff like that, what we're worried about is bridging the surface to the subsurface and short circuiting that horizontal flow. So we had to put in our best approach there was at least to develop a particle size distribution, which we did, which it updated in our new specification that has some tolerances for too big of material and some tolerances for that particle range of what that material should be. Again, it's a work in progress. This is not a it's exact science, but it should be, you should have an eye on that material with not allowing vertical infiltration over the long-term operation of the system. Okay, so the soil testing, again, we used to prescribe like phosphorus index or other things that really done in an agricultural lab, but UVM has really helped us update this, and we're stealing this directly from the bioretention and gravel wetland soil specification that Jill showed earlier. So that will be in our spec coming out soon. And it just requires more of the Mehlich-3 and the evaluation of the soluble reactive phosphorus component to be. And the idea there is we don't want those soils contributing to excess phosphorus. So vegetation is the other really difficult piece here. We have opted for seeding it just because these wetland soils come from all walks of life. They're in all different locations, right? Some are shady, some are sunny, and purchasing a seed mix is probably the most suitable for self-selecting the wetland plants that will grow. We have accepted gravel wetlands that were temporarily stabilized with like a contractor mix. I think that's fine, but over time we'd like, obviously this should be functioning with wetland plants, and the beauty of a system like this is obligate and facultative wetland plants can grow in a system like this and can benefit overall pollutant reduction. So just a very quick, I know my time's running out. We had done in our original installation, we had done lots of plugs and wetland plants, potted wetland plants. And we found about 53% of the planted species were still present, which is good, but that means 47% of what we planted, which is probably about a $20,000 planting pallet, had just disappeared. So they're a mix of obligate and facultative species. And then the key to eliminating, I think, some of the more invasives, which may come in, is having that early, dense vegetation before that system comes online, making sure that the vegetation is dense and well established in the system. Other questions that have come up over the years, are with respect to ponding depth. One of the benefits of a system like this is you can potentially deal with those peak flow controls and have more storage area available for the larger storm events because it is temporary. So we don't really have guidance. I think guidance on the ponding depth is really goes back to sustainability of the plant species that are selected. So again, more ponding means that's going to selectively control what plants are going to be able to be sustained in that system. So our system itself that was tested was 18 inches ponding, which is, I guess, where we settle in on that preferable level. But again, this is somewhat flexible, and I think it's more akin to what you're planting the system with. The water quality volume storage, the question is it static or dynamically sized? It's a statically sliced volume in the above ground basin geometry. So we don't count the available storage space in the saturated stone into the design storage volume, only because it's saturated. And for the most part, we found that to be true even in the hot summer months where we have long periods of time when we don't have rain. We still have a significant amount of water in that saturated zone. So we don't count that towards the design for the water quality volume or the design storage volume. So next, how important is a two-cell treatment approach? Again, we've had long conversations with our alteration of terrain program at our Department of Environment, and I'm pretty comfortable that any single cell subsurface gravel wetland will be far superior than most other treatment systems that would be allowed. Definitely compared to like a detention or a retention pond. So I don't have any issues with a single cell, although, you know, you might run into some issues with people wanting more data. And I would love to have more data, but we just don't. So is there any specific reason for the 15-foot flow path? That was just something we did some initial testing early on, and we found a 30-foot flow path across the whole system was really important for that plug flow and the water quality function that we wanted to achieve. That was just based on some simple sluice testing early on. So the 30-foot travel length is the key. Whether you have one cell or two cell combined, they should be a minimum of 30 feet travel through the gravel. And then with respect to that maintaining, we had long conversations with our AOT program early on about, you know, do we tap into the groundwater table, which is often a technique in order to keep like a retention pond, maintaining a water level. It's really not necessary. We found even in dry months, so this is basically water level over time. The upper dotted line is the top of the water quality, top of the wetland system. So that's top of soil. The green line is the orifice invert. So this is where the water should be inter-event at all times along the green line. And then the purple is the bottom of the gravel. So you've got, you know, what we see here is that even in the driest of months here in the middle of July, we at most only have a half an inch of evaporation within the subsurface storage reservoir, which exists between the top of the gravel here and the bottom of the gravel. So this is our internal storage reservoir. And so the question is, do we need to do something? Do we need calculations to show that the water levels aren't going to drop? And the answer is that there is some drop, but we're always maintaining over 1.5 feet of water in the saturated zone, which I think is fine for maintaining that anaerobic condition. And then last but not least, just in the last 3 minutes that I have, we just wanted to go over, we have, so what do I do in a nitrogen impaired area in a coastal environment where I want to use a gravel wetland, but I have good soils. And that's really where we came up with this hybrid design. And we have a at least a CAD drawing of this on our website. This is relatively new in that I haven't seen too many implementation schemes of this. We have seen a couple, but essentially what we're doing is we're creating this kind of a plug flow path through the primary flow path within a system. So in this depiction, you're seeing this hybrid system is the entire system. But again, we think of it like this could be nested within a gravel wetland style system. So I'm not going to go over too much of the details. It's all included in that hybrid design spec, but I will, sorry, I'm having trouble with the, I will, this is an instance where this was installed because it was in a coastal environment. So alteration of terrain wanted them to do a hybrid system, but it was in like a B soil. So we didn't want to completely line the whole thing and eliminate the, the infiltration capacity of those good soils. So essentially think of it like here's the bioretention system. I know CAD drawings are hard to read, but our gravel wetland system is nested, in this primary flow path within the bioretention. So bioretention, and then here, this T section is what is essentially nested within that bioretention. So that creates the first flush, and the primary flow path goes through this gravel wetland, and then anything else kind of spills out of the bathtub and goes through your typical bioretention style treatment practice. So it's really the best of both worlds. We did install one and monitor it in the Cape, which is the most suitable spot for something like this, the bathtub hybrid system, and it performed wonderfully. And when we looked at the performance, and we have a whole report on that, but it's almost like you got a compound performance curve of an infiltration basin with a gravel wetland. So you got the benefits of both of those systems. So it really worked out well. We were happy with that. That was for EPA Region 1, and I think we must have that report is somewhere on the web. You can email me. I can send it to you if you want to look at it further. But I think that's about all the time I have. This does require maintenance, and that maintenance really is harvesting of the vegetation, not pulling it out, but like cutting it back. And I think that's probably one of the more problematic aspects. This is our gravel wetland. This is the forebay, which was really functioning and designed being wet. And here are the two subsequent gravel cells. But because these are dry, we can, at least with students, we can get on there and harvest that material. And that's really the long-term maintenance. Every 3 years, 3 to 5 years, we're harvesting that and composting it kind of outside the system. So I think I'll end there, and I think I'm right on time. Oh, 1 minute over, sorry.
Thanks, Jamie. You just want to stop sharing, and then Jane can share things. Thank you, Jane. Awesome. Thank you, Jamie. That was a great presentation. As Chloe mentioned, I'm just going to briefly go over some funding options that are available for communities who are looking to fund some of these stormwater and green infrastructure projects, primarily through the Clean Water State Revolving Fund, but I'm also going to briefly touch on a few other grant opportunities that are New England state specific.
Give us just a second, Matt. We'll get those, or you can go ahead. We'll get those slides in full screen. Keep going.
Oh, sure. So I know a lot of people on the webinar are probably already familiar in some way with the CWSRF, but for those who aren't as familiar, the CWSRF, it stands for the Clean Water State Revolving Fund. And it's basically a federal state partnership program that helps communities pay for water quality improvements, but at very low interest rates. It was originally established with federal funding from the EPA. Over time, states continue to get new federal dollars each year, and as old loans are repaid, that money revolves back into the fund. And so each state's environmental agency runs its own version of the program. And so that means the priorities, interest rates, and application process can look a little different from state to state, which can make it a bit confusing just depending on what state you're in and what state that you're applying to. And although most projects funded through the CWSRF have a focus on wastewater treatment plant upgrades or improving aging wastewater infrastructure, it's not just for wastewater. The CWSRF can also fund stormwater and non-point source projects that improve water quality. And so some eligible stormwater uses include green infrastructure, things like wetlands, bioretention, or infiltration systems, retrofits to fix existing runoff problems, and even project planning and design, not just construction. And so the CWSRF loans, they usually have below market interest rates, often just 1 to 3%, and repayment terms are often very favorable as well. They can range from 20 to 30 years. And so that amounts to huge savings compared to traditional borrowing. And so, many states can even offer principal forgiveness and other subsidies for projects that meet priority goals, or if your community has disadvantaged criteria that they meet. And a good example of this is in the New England state of New Hampshire. They have forgivable stormwater planning loans of up to $100,000, and which is just a great tool for communities just starting out to plan stormwater projects and may not want to take that next step. So next slide, Jane, whenever you can, sorry. And so a good example of using the CWSRF for some of these projects that also includes a gravel wetland is back in 2020, the Hadley Road Area Infrastructure Project in South Burlington, Vermont. Vermont CWSRF program has a special feature where it lets communities bundle green infrastructure like gravel wetlands into larger wastewater projects. And so when they do that, they can qualify for grant equivalent funding for the green portion of that project. And so in this case, South Burlington added a gravel wetland to treat stormwater runoff as part of a wastewater and stormwater separation project. And because they included that green infrastructure piece, the state awarded them a $298,000 loan that was fully forgiven, basically turning that portion into a grant. And so with that setup, we're adding green stormwater infrastructure can then trigger loan forgiveness. And although it is unique to Vermont's program, it's just a good example of how having that great incentive for communities allows them to think about green infrastructure as being an integral part of their SRF eligible projects and not just an afterthought. And so a big part of our Newen team goal is to try to help communities all throughout New England look at their SRF program in their specific state and try to see what sort of incentives are available to help them try to create these bundle packages to try to unlock as many incentives and create as good of a package for them as is possible. Next slide, please. And so next, I'm going to quickly touch on another grant funding program that is available in all New England states, but I'm going to speak more specifically about the program that's available in Massachusetts. And so this is the OSG program, the Sewer Overflow and Stormwater Reuse Municipal Grant Program. And so this is funded by the EPA, but just like the CWSRF, it's managed at the state level. And so that means municipalities apply directly to their state environmental agency, not to the EPA. And so how that works is the EPA gives each state an allocation of OSG funds, and then the state distributes that money to local communities. So cities, towns, or utilities who are eligible for sewer overflow or stormwater management projects. And so the main focus is on projects that reduce sewer overflows or improve stormwater systems. And so in Massachusetts, their OSG program is especially valuable for early stage stormwater work. It can provide up to $250,000 for planning and design before construction even starts. And so it's important to remember that this is grant money, it's not a loan. And so unlike the SRF fund, there's no repayment required. And so that really makes the OSG a perfect fit for communities that don't yet have a full design or don't have a funding strategy yet put together. And so it helps take an idea or a stormwater concept and it moves it to what we like to call SRF ready status. And so the OSG program also typically gives priority to disadvantaged or smaller communities, typically those with a population of under 10,000. Next slide, please. Next, I'm going to speak very briefly and also a little bit more generally just about Vermont's QUIP grants, which stands for Clean Water Initiative Program. And so this is Vermont's main grant source for stormwater and water quality projects. And the first thing to know, this is not alone, it's grant funding, which means communities can make real progress on water quality projects without taking on new debt. And so what can QUIP fund? It can fund a pretty wide range of stormwater improvements, including green infrastructure retrofits, stormwater system upgrades, and wetland restoration or other nature-based solutions. And so it's a really flexible program that covers both traditional and green stormwater approaches. QUIP is a great fit for smaller projects or for work that doesn't necessarily fit neatly into a CWSRF loan. And so the program, it also usually has multiple funding rounds each year. And so communities might not necessarily have to wait long to apply. And it works well for, both at the concept level for projects, the early planning and design phase, and there's also opportunity for more implementation ready projects that are ready to build. So again, it offers that good flexibility. And in many cases, you can pair QUIP with CWSRF funding. So QUIP might cover the green infrastructure elements, the parts that directly improve water quality, while CWSRF helps fund the larger infrastructure components of the project. And so just to wrap up, so please feel free to get in touch with our new team if you are looking for assistance. Helping communities navigate these funding sources, especially the state revolving funds, is just one of the key services that our program provides. And so through our regional network of partners, we're able to support communities in a lot of different ways, things like asset management, financial reviews, rate analysis, and even income surveys. All of these services are designed to help communities understand their needs and strengthen their financial position. And so our goal is to really assist communities through that entire process, from early planning and assessment all the way to submitting a successful funding application. So feel free to contact us if there's a project that you feel we may be able to assist you with.
Thanks so much, Matt. And thank you, Jamie and Jill, as well. We have a little over 5 minutes left to answer your questions. So if you haven't already, feel free to drop those in the Q&A feature. And our presenters can stay on a bit after 1 too, if we need to. Just to flag again, we will share the recording, and we're also dropping into the chat a short feedback form. It should take you just a minute or two to give us some feedback on this webinar. So thanks for your time, and I'm going to hand it over to my colleague Laura to pose the questions to our speakers.
Thanks, Chloe. Our first question is, is there particular importance of using slotted underdrain as opposed to perforated pipe? This was about, I'm thinking the first for you, Jamie, in the first half of your talk.
I think it's your preference. You know, slotted tends to be slits along the pipe in every direction. The perforated or kind of drilled pipe typically isn't in all directions, and those should be pointed up, if you will. So, you know, the bottom of the pipe should not have the perforations. The water needs to rise to enter into the perforations. So we haven't identified pluses or minus with either. I think it's your preference.
Thanks, Jamie. Our next question is, what types of reconstruction activities have been needed at the UNH Gravel Wetland or other sites that you studied that have been online for any length of time?
Reconstruction. I'm not aware of reconstruction. I think a lot of the long-term maintenance issues are with respect to the the harvesting of that vegetation. Again, that's something that it is likely is likely difficult for the long-term operation. The reason why we do it is because in studying the system, we found that within 3 years, that, if you think of the retention in the biomass of the nutrients, that will, through, 3 or 4 winters, will eventually go from organic form to inorganic form, and it'll start to disrupt your mass removal balance. So, that's one of the reasons to maintain a positive balance. We wanted to do that. I don't think there's that level of monitoring in constructed systems. So it's one of the maintenance criteria we put forward. But again, maintenance is kind of the 1,000-pound gorilla in the room, right? So I forget what and then the outlet structure, I think. Oftentimes when you walk by a gravel wetland and you see it ponded for more than 48 hours, then there's the probability is that orifice control, the primary flow control, is clogged. So, it's as simple as reaching your hand in and pulling out a glob of organic material.
On the thread of maintenance activities, this comes from someone who has significant invasive species pressure. What is the recommended mowing schedule of upland slope areas and wetland cells to maximize function and habitat?
I think so. You're getting into areas beyond my expertise. Maximizing function and habitat. I don't have an answer to that. I mean, we're talking about a 3 to 5 year kind of mowing in order to maintain the positive nutrient removal balance. Presumably that would be disruptive to the ecological function of the system and the habitat. And this is another kind of interesting component. We fought pretty hard in New Hampshire to get these constructed wetlands off of any type of statutory wetland list, so that they're not treated as a statutory wetland, so that we can maintain it. I think it still remains to be seen. There was a controversy a while ago where a old wetland system had never been maintained, and they just went in after like 20 years and maintained it and disrupted a lot of nesting birds and other wildlife and the ecology that had established itself over those 2 decades of no maintenance operation. So I think it's still, I mean, there are guidelines, and we have that in our state manual that you need to follow. Like, you can't just go into you couldn't just go into even a constructed wetland and maintain it any time. It would need to be, oftentimes you consult with your Fish and Game or your wildlife, and make sure that you're not in a sensitive time of year. So I don't know if I answered your question or if I successfully avoided it. There's a lot that I can't really answer with respect to, the ecological function of a wetland.
Thanks, Jamie. And for everyone, we have a couple more questions, and we're happy to stay on for a few extra minutes. So if anyone has any additional questions, please keep throwing them into the Q&A. This is also related to vegetation. Can you confirm that the harvested vegetation should not be left in the gravel wetland?
Yes, I can confirm that. So, and this essentially, it would go with any system. Even if you were maintaining or pruning a bioretention system, you wouldn't want to cut that material and leave it there to degrade. Like, you'd want to compost it outside the system, and then potentially it could be part of another kind of nutrient cycling. So we know a lot of DPWs also have composting features at their transfer station, where organic material will be reduced to compost that residents can use on their gardens. So anywhere outside of that system, it is the best.
Great. We have, let's see, one more, oh no, we got some more, but the denitrification process is critical for nitrogen-limited aquatic ecosystems. What have you found for the phosphorus removal mechanism for phosphorus-limited aquatic ecosystems?
So for phosphorus, the challenge always is um, absorption. And what we found, and the UVM found this as well. So we found this early on. I think UVM just graduated a PhD student who also published on this, that showed introduction of compost into the bioretention soil mix led to leaching of phosphorus. And so we find it very challenging to, again, keep that phosphorus in the system. And especially if you're loading it with a compost, then it's even more challenging. So that has led to the introduction of media amendments, which I think is one exciting area, emergent area of science. And again, UVM is published on the use of water treatment residuals. We've published on, or at least had grad students develop thesis on use of water treatment residuals. Very, very effective. And these are kind of the alum from the drinking water treatment process. If you dry that out, it's very amendable to soils, and it can provide up to 20 years of phosphorus scavenging in these systems. So suffice it to say, phosphorus is challenging, even in these media systems. I think infiltration, we tend to think that infiltration, kind of that phosphorus disappears, right? Because phosphorus is not highly mobile in the native soil environment. It forms mineral complexes, and it doesn't necessarily move quickly through soil. So infiltration, at least up till now, has been deemed a removal pathway for phosphorus. And then if you're looking to manage phosphorus within a system, at least eliminate the compost out of that bioretention soil mix.
Thanks, Jamie. If lateral flow is the goal, why avoid geotextile layers between the gravel and native soil, even if it tends to clog?
Yeah, it's a good question. The reason being for this application is the fear of limiting the roots from going into that saturated zone. So again, these systems haven't been largely studied. I mean, we just did a deconstruction study on our system. The focus was on, a lot of the physical properties. We did do an analysis of in the stone of the root penetration and the root density. I have yet to fully digest that, but the speculation is the roots get into that area and are also available substrate for bacteria, and that there's all kinds of beneficial processes happening, microbial and otherwise, happening in that rhizosphere of the root. So the fear would be a textile would limit the root penetration.
All right, I think we have time for one more, and this is related to the phosphorus question, I believe. Is the anoxic conditions the driver for dissolved phosphorus output?
Is anoxic conditions is the driver for denitrification, microbial mediated denitrification. I don't believe, I don't know what the redox condition does for phosphorus. Once phosphorus binds, it binds pretty competitively. We do see some recycling of the absorptive capacity of the subsurface substrate after winter operations. And I guess the speculation is that might have something to do with chloride kind of stripping the absorption sites. We don't see an attendant release in phosphorus in the winter, however, which is somewhat curious. And so it's one of the next things on our agenda is to study the impacts of chloride to the absorption processes in these types of filters. So, but the main driver for phosphorus removal, soluble or dissolved or particulate, is going to be absorption to that organic material.
Thanks, Jamie. And thanks for those of you who stuck around. I think we'll end there. I know there's a question from a more detailed question from Andrew Mills in the chat. So Andrew, if you want to reach out to Jamie directly, I'm sure he can respond to that, but we appreciate your time. And we'll send around again our quick feedback form and recording. Thank you so much. Enjoy the rest of your day. Bye.